Structures which interlock to infinity. That's how the universe appears to us when we view the chain of the infinitely complex, the chain of the infinitely great, or of the infinitesimal. One of the aims of contemporary physics is precisely to reach the ultimate links of the imperceptible, to observe matter at a millionth of a billionth of a millimeter. In this plunge into the subatomic universe, dimensions shrink at breathtaking speeds. Diameter of this drop of water, 5 millimeters. Diameter of a molecule of water, 10 millionth of a millimeter. Diameter of an atom nucleus, 1,000th of a billionth of a millimeter. How simple our vision of matter seemed in the early 1930s. Its smallest components were the proton, the neutron, and the electron. But discoveries of new particles were soon on the way. The positive electron, muons, pions, kaons, very heavy particles and a profusion of new particles, odd and ephemeral, over 300 in 1965. To the fundamental discovery of the 1970s, which can be summed up as follows. There exists a still more basic level of particles, which form protons and neutrons, and a large number of fleeting particles, the quarks level. Thought today that there are 6 quarks with different natures, or savors as they're called. Their names are up, down, strangeness, charm, beauty, and truth. Each bears a fractionary electric charge. Inside the quark family is the lepton family, the electron and its 2 siblings, the muon and the tor, both more massive. Then associated with each of them, 3 charge-free particles, the electron, muon, and tor neutrinos. Matter is built with leptons and quarks. Physicists would know nothing of the world of particles were it not for experimentation. They have the choice of 3 approaches. First, to wait for the opportunity to observe a spontaneous phenomenon. Nuclear physics came into being at the turn of the century through the simple observation of radioactivity. However, physicists also make use of accelerators to hurtle projectile particles against target particles so as to blow them to pieces and examine their fragments. Physicists can also use some projectiles as fine probes of the internal structure of the target. These investigation techniques must take into account certain particle characteristics. For example, sensor particles behave as waves, and the shorter their lengths are, the greater is their energy. To perform a fine analysis of a tiny object, particles with a short wavelength have to be used. If particles with a long wavelength were used, the optical phenomenon of diffraction would prevent us from seeing the details. Here are some examples of this necessary adaptation of the sensor particle to the target particle. Alpha particles of 5 million electron volts were all Rutherford needed to discover the nucleus of the gold atom. But protons of 300 million electron volts were needed to make out the neutrons in an atom nucleus. Today, electrons of 10 billion electron volts are required if quarks are to be viewed within the proton. The more one explores the infinitesimal, the shorter the wavelength of the sensor particle must be, and the greater its energy. That's why experimental tools have become increasingly powerful. The latest of these devices, which serve to trigger extremely violent collisions between sensor particles and fragments of matter, have also made an amazing observation possible. Particles are created during the collision. Photographs show not only the sensor and target particles, but also a large number of other particles created by the energy resulting from the collision. Particles come together to make up matter. But what keeps them together? What governs their organization? What makes them come into being, live or die? These are the four basic interactions. The weak nuclear interaction, the strong nuclear interaction, the electromagnetic interaction, and the gravitational interaction. Gravitation is attractive between all the masses. Its range is infinite, but its intensity is by far the weakest of the four interactions. It's preponderant only at the cosmic level. The electromagnetic interaction is attractive or repulsive and occurs between the electric charges. Its range is infinite and its intensity is 10 to the power of 38 times greater than that of gravitation. It ensures the stability of atoms and molecules. The strong interaction is attractive and 100 times more intense than the electromagnetic interaction. It cements the quarks which form the particles, like protons and neutrons. In the nucleus, the cohesion between neutrons and protons is but the residue of this force between quarks. Lastly, the weak interaction is 100,000 billion times weaker than the strong interaction. It occurs at the nucleus scale in beta radioactivity phenomena, or in certain nuclear reactions, such as the fusion of hydrogen in helium in the core of the Sun. Gravitation and the weak interaction act on all the basic particles, which is not the case for the two other interactions. The strong interaction acts on the quarks, but not on the leptons. The electromagnetic interaction acts on charged particles, but not on neutral ones. A neutrino, thus escaping from these two major interactions, has such little chance of interacting that it can pass through the Earth without being stopped. If there's to be interaction between two particles, a parcel of energy must pass from one to the other. However, this exchange is a breach of the principle of the conservation of energy. So, to explain the interactions, physicists believe that there are deviations from this principle, virtual processes in which the stronger the energy fluctuations are, the briefer they are. For example, the energy fluctuation may reach 10 to the power of -5 of an electron volt if it occurs in less than 10 billionths of a second. It reaches 1,000,000 electron volts if it occurs in less than 10 to the power of -21 of a second. It can attain 1,000 million electron volts if it occurs in under 10 to the power of -24 of a second. These virtual processes are unobservable by definition, but their effects can be observed. They bring into play hidden particles that physicists endeavor to uncover through new experiments. The interactions between particles of matter can be considered as virtual exchange processes. And in these exchanges, there are rules, just as there are in tennis. For instance, each particle must possess a characteristic predisposing it to the exchange. According to another rule, in all interactions there must be an object exchanged between the particles, a messenger called a boson. Bosons are not all particles of matter, but are nonetheless genuine basic particles. They function as go-betweens and as such are virtual. But they can also be produced during collisions, and in this case are identifiable. Particles of matter are always produced in pairs, particle and antiparticle, whereas any number of bosons can be created. The interactions each have their predisposed characteristic and messenger. In the strong nuclear interaction, which ensures the cohesion of quarks within the proton, the predisposed characteristic is called color. Quarks have it in 3 states: blue, green, or red. The messenger is the gluon. It switches the colors between quarks by conveying 2 color charges. One cancels out the former complementary color, and the other is the new color. In particles made up of quarks, the colors of the quarks are perfectly compensated. The particles are said to be white. This white symbolizes the cohesion provided by the strong interaction. It illustrates the indissociable character of the quarks. If colored, they cannot be isolated. The experiment proved that when one tries to extract a quark from its particle, the energy provided produces new particles. If the energy is substantial, the reduction increases, bringing forth jets of hadrons.
So it can be decay of heavy quarks.
The recent discoveries of the W and Z0 bosons at the CERN have confirmed the unification of the weak and electromagnetic interactions, and have opened the way to generalizing the unification of the interactions.
Yeah, but the jet carries an electron. Yeah, candidate electron. It's something which looks like electron, to the better you know.
At energies of about 10 to the power of 30 electron volts, the 4 interactions fuse into a single force. Only by going down the energy scale do they separate one by one. Gravitation is the first to separate. Then comes the turn of the strong interaction, followed by the weak and electromagnetic interactions. The familiar landscape of interactions is to be found again below the 100 billion electron volt level. One of the verifiable consequences of this unification might be the disintegration of the proton. Unfortunately, this is a rare event indeed, and difficult to observe, since it occurs on the average once a year and per 1,000 tons of iron. And yet no effort is spared to view it in huge underground detectors. In their research into the ultimate components of matter, physicists constantly perfect their models and put them to the test in experiments. To go beyond the scale of 1/1,000,000th of a billionth of a millimeter, they'll have to invent other tools and perhaps other theoretical models. The search for elementarity is an endless quest.